We're going to talk about forest biomass estimation. I assume everyone knows what LIDAR is. This is like now common knowledge, especially among this group. So we're getting LIDAR data delivered as a point cloud. And it's not, only maybe this month is the capacity to resolve individual trees available to us. Up until now, we've had to handle point data by aggregating it to some arbitrary unit. Because if we talk about the scale of the biomass process, it could be the individual tree, it could be the stand, it could be forest management properties. We don't exactly have a good sense of what the scale of the forest biomass process is. But the points, what we do know is that the individual points have no mass. They're just non-dimensional. So we need some way to turn those points into a volume to get mass, which is a volumetric quantity. And the way that's been handled is to fix an area on the ground, either a disk or a square cell, and then form a three-dimensional volume, either a cylinder or a rectangular prism, and vary the height according to some statistics computed on the LIDAR points. It could be mean, max, could be things like decile cutoffs, or there are these density fractions. We have about, I think, 32 commonly used LIDAR summary statistics that set the top of that volume. And so the question that naturally always arises is, what's the right size? What's the right size to fix that footprint at? Now, I happen to be working on a project in Norway where we had a historical reason to choose 400 meter square plots, because that's where we had forest inventory plots. They send foresters out to the field. They measure the biomass on the plot. Actually, they estimate it using allometric equations. But we treat the values on those 400 meter square disks as known. And if we're using a model-based situation where we want to make prediction, we also can grid the study area into a grid for prediction. And so what's the right size if you didn't have this historical reason, if you were designing a new study, if you were starting from scratch? What's the best choice for how big to make the plots, how big to make the grid cells? And one answer is it's a lot cheaper to go collect fewer larger plots, because you're only sending, the foresters out to certain locations. Now, forest inventories have been done for over 100 years. It's a field with a lot of history. And until maybe 20, 30 years ago, most of these were conducted in an inferential paradigm that we're calling design-based. This is sampling. So you would take the, known biomass on those plots and use an estimator equation depending on the situation when you collected those plots, that would give you an estimate for the whole forest, and it would also give you a variance of that estimate. And the variance would be some indicator of how precise the estimate was. And under this inferential paradigm, the source of randomness is in the likelihood of choosing that particular plot out of all of the space available to you. You can think of it as trying to estimate the weight of a brick wall. It would be helpful to have sampling units that were very uniform. So if you got 6 bricks out of this wall, you knew there were 30 bricks, you weighed them, you got an estimate. And then if you went and chose another 6 bricks, the estimate would likely be very similar. So in this paradigm, low variance between your units is a good thing. And if you found yourself in a situation where you had high variance for some reason, you would try to group your data in such a way to sequester variance within the units so that the units were uniform with respect to one another. For example, if you had soil anisotropy, you might run a transect across it in a way that you want to capture as much variance inside and make the transects very similar to each other. So this was the prevailing wisdom. And now, as we come into, the model-based era, we have model-based inference, where the presumption is that there is some underlying process, and the randomness comes in where we are taking examples of that process. So the entire source of inference is different. And what we find in regression is that you really don't want low variance among your sample units, because you want to measure things that are very small and very large so that you get a large variety of x's and you can get a good regression. Now, if you run a regression with low variance among your sample units, this is the modifiable error unit problem. It can inflate correlation. If you choose your units in such a way, or you make very large units that sequester a lot of the variance, you can inflate R², you can inflate other indicators of model quality that are scale dependent, like RMSE. So I put in these two graphs from recent papers. This one shows on the x-axis something you can think of as LiDAR height, and on the y-axis a correlate of biomass, and you can see decreasing or increasing grain size as you move through the graphs, and how much information is lost when you have fewer larger plots. And a statistics friend was laughing with me, why didn't they just use 2 so they could get an R² of 1 and an RMSE of 0? And then this graph came from a recent paper. It shows plot size and R² going up, plot size and RMSE going down. And when I first saw this, I was reminded of the almost identical graph in Fotheringham and Wong. And this is currently being propagated in the field as advice for how you should design your study plan. That's it.
Questions for Jill while we switch? Yeah, go ahead.
Usually when we're looking at density, we're interested in points per square meter for the LiDAR, as well as whether you're getting first or second returns.
Right,
first,
I'm
but
suppressing
the
a lot.
multiple returns, because that gives you
I mean,
an
each-
indication of the density of the canopy. So I'm just, and also with that high a density that we can get now, 50 points per square meter, you can actually look at the morphology of individual trees.
Sure.
Just wondering if you played around with that.
We have used density fractions, and I will say that density fraction, this is forest density above the 10th decile, et cetera. They are somewhat more robust with respect to loss of variance than, say, mean, but they do still experience it somewhat. I don't want you to get that confused with what this was, carbon density. That's a different concept. But we have about 130 LiDAR first or last returns per 400 meter square plot. So it's quite a lot of data, even within a plot. This is airborne LiDAR.